All right, part two of these rational functions. So I have the same one. I left them unfactored for this horizontal asymptote because we don't really need it. And in fact, it's a bit easier to see it at the original function, the original way that is written, non-simplified for horizontal asymptotes. All right, I have three cases on the right here, and I just wrote n greater than d, n equals d, n is less than d. All right, when I say n, what I'm referring to is the degree of the numerator versus the degree of the denominator. So the n and d, really I'm just saying numerator, denominator, but it's not necessarily is the numerator larger, it's the degree of the numerator. Okay. I'm going to go backwards. I'm going to actually start with the third one, and which would be case 3, and then explain each of those going backwards, case 2 and case 1. All right, so if we look at these, and usually they're written in descending order, but if not, it's important to look at the degree, not the first term. So I have a degree 3 in the denominator and 2 in the numerator, right? So therefore the degree of the numerator is less than the denominator, and that's case 3. I'm going to explain what the rule is and then why this rule exists as well to make sense of it, because I don't think it's something that you need to memorize. And for those moving on to trig and calculus, you're going to see this called something else, a limit as we go to infinity. But for now, that's not that important. All right. The idea is what we're looking for. So for a horizontal asymptote, if the degree is larger, if the numerator is less, then we get one. We get a horizontal asymptote at y equals 0. Okay. Now let's look why. Why is this true? Picture x is getting larger and larger and larger, right? Like we're going to infinity. And that's why in calculus we say the limit as x goes to infinity. But anyways, x is going to infinity. It's getting extremely large. And we could also apply negative infinity. But for simplicity, we'll go infinity. If we look at a power of 10, right, 10 squared, and I talked about this in another video, that these smaller things don't really compare to the larger exponent here. So we're just going to look at 10. If I looked at 10 squared opposed to 10 to the third, right, the denominator is 10 times larger. Not that big of a deal yet. But now let's plug in like 100 squared versus 100 to the third. And yes, there is this 2, but in the long run, a 2 multiplied by that isn't going to be that big of a deal. Okay, 100 to the third is there, 100,000 compared to 1,000. And then again, we have some other stuff, plus or minus some other stuff, right? All right, now this denominator is looking much larger at this point. I only went up to 100. I mean, picture 1,000, 10,000. We're going larger and larger. Sure, the numerator is getting quite large, but this denominator, right, is far larger. And it's not just a power of 10. It's a power, right? It's a whole additional exponent. If I had a million squared, that's a million times a million. But a million to the third, a million times a million times a million, it's a million times larger. But we are going to infinity. So point being, you could tell already that if I take something small and I divide it by something large, extremely large, right? It's tending to 0. Okay, we're going to 0. If I take $1 and I split it up to 1 million people, right? I mean, you could keep my portion. We're all getting nothing, really. So that's the way I like to think of it. Or if you're great at memorizing rules, know that if the degree of the numerator is less than the denominator, there is a horizontal asymptote, and it is y equals 0. Okay. Case 2, as I said, working backwards. If the degrees are equal in the numerator and denominator, then what you do is you look at the leading terms, so we have, in this case, just x squared over x squared, and you divide their coefficients. So I'm just going to write a over b, so that is the horizontal asymptote. And what does that mean? That means like the coefficient here is a 1. Whoops. Okay, the coefficient here is a 1 and the coefficient here is a 1. So the horizontal asymptote is just y equals 1 over 1, which is 1. Jumping back really quick, I should have wrote this one here. The horizontal asymptote is y equals 0. Okay. All right, this one it is y equals 1. If this problem changed a bit, like say I had 4x squared in the numerator and just x squared in the denominator, then the horizontal asymptote would be 4. If I had 4x squared with stuff and then 3x squared with stuff, then the horizontal asymptote would be 4 over 3. All right? You just take the leading terms and you divide their coefficients if the degrees are equal. And I erased too much. That's okay. Alrighty, so we had 1 over 1. Horizontal asymptote is 1. Easy case. Now, this last case, technically it is the easiest, but there is one time when it is not. If the degree of the numerator is greater, there is no horizontal asymptote. All right. Even in the special one case I'm talking about, there is no horizontal asymptote. Why is that true? Picture this one. Now we have the reverse of the third, right? My numerator is getting extremely large. Like, I'm just going to throw in a whole bunch of zeros. Okay, and then divide it by some zeros. Now, if I say, take $1 trillion and split it up among 100,000 of us, I'm not giving away my share anymore, right? I like that. As we go to infinity, this thing is unbounded. The top, the numerator, just keeps growing larger and larger and larger, divided by something small. So therefore, it goes to infinity. And that means like this graph, whatever it's doing, it just keeps growing and growing and growing. Okay, there is no horizontal asymptote. All right, so no horizontal asymptote for this one. But there is one thing, it's called an oblique asymptote. We won't do a whole lot of it. Time pending, that is. So if there is enough time, we may look at how to divide polynomials and look at some root test and whatnot. But for this video, I'm going to keep it somewhat short. I'm going to show how to do it, but we're not going to get into a ton of different examples. Here's what an oblique asymptote means first off. So an oblique, O-B-L-I-Q-U-E asymptote, it's not horizontal, it's not vertical, it's like a line, right? If I were to have a graph and I graphed a line as an asymptote, so how is that possible? Well, maybe this graph does something like this, okay, and it approaches that oblique asymptote, or sometimes it's called a slant asymptote, okay, but it will never cross. Okay, those asymptotes exist as well, but they only exist if the degree of the numerator, so if the numerator is equal to the degree of the denominator plus 1. So if it's 1 larger, and looking here, we can see that is in fact true, right? The degree of the numerator is 2, and the degree of the denominator is 1. So the degree of the numerator is 1 larger than the denominator. There is going to be a slant asymptote. How do we find this? You have to use polynomial long division. So what does that mean? We take x plus 1 and we divide it into the numerator. Like I said, we don't do much division, kind of time permitting in this course. But if we do have time, we will look at more division later. So I'm going to keep kind of a long division, some random numbers off to the side here to show how it kind of relates. Okay. If we ask 13 into 6792, 6,792, how you do it by hand is you say, all right, 13 doesn't go into 6, right? But it does go into 67. And that would be, I believe, 5 times, I think. Okay. So same thing here. We want to line up our answers. So we look at, and one other way too, you kind of like, when you're doing this in your head, the uglier it is, you kind of start to round, right? Say this was 132 or something. You'd probably kind of think like 100 or 130. Here I'm kind of thinking 10 to 15-ish, right? Same thing here. I'm looking at x only into x squared. So x multiplied by something would give me x squared. X multiplied by x would give me x squared. And a way to check that, well, two ways, I guess. You could just do x squared over x. This divided by this would give me x. All right, that's one way. Another way, just like when we do our division with long division with numbers, I now go 5 times 13. So I would go 5 times 3 is 15, and then 5 times 10 is 50, 60, right? And then I subtract. Do the same thing here. X times 1 is x. X times x is x squared. And then I subtract. So I change all the signs. Now, looking at the right, I would bring down the 2, and 13 cannot go into 2, so I did good. But then I have to bring down the next number, right? Same thing over here. X squared minus x squared is 0. That's good. But negative 4x minus x is negative 5x, and I need to bring down the next number. Okay, then we just continue. 13 into 29 goes once. 1 times 13 is 13, and I subtract. Right? I brought down the next number. So here, x into negative 5x is negative 5. Notice my x's are lined up. My numbers are lined up. The x squareds are lined up. Right? I want to keep everything in order just like I do here. So now negative 5 times 1 is negative 5. Negative 5 times x is negative 5x. But remember, we are subtracting, so that means we switch all these signs. Negative 5x plus 5x, 0. 3 plus 5 is 8. Now x cannot go into 8, so therefore this is the remainder. Before we finish this one and let me explain how to do that, let's look at the similar 13 over here. So one thing I just noticed is 29, I should have done 2, because 13, right, I get 16, I screwed that up. It's a good check. So 26, and then I had to subtract 32. So 2 is 26, and a remainder of 6. All right, this remainder, we say 6 over 13, right? The remainder over what the original divisor was. So I have 8 plus 8 over x plus 1. Here I had to write plus because it would be weird to just write 8 over x plus 1 right after this minus 5. Where here 522 and 6/13, we don't really need to say the plus, right? Okay. You will have very limited oblique. I think there's only one or two in your homework, and they shouldn't be too hard. But your answer is this. You don't worry about the remainder. I just wanted to finish it off. The oblique asymptote is y equals x minus 5.